I appreciate that, Shay. So I want to start with a labeling convention. It's very common to label of vertices of in triangles or in other parallelograms or other diagrams. Label vertices with capital letters. And for triangles, it's really common to label the side opposite a particular vertex or a particular angle with the lowercase letter that corresponds. So this angle A is opposite that side A, this angle B being opposite side B, and angle C, where that's a capital C, is side lowercase c. You'll sometimes see your book label these as alpha, beta, and gamma, but it doesn't change our tool. Actually, the labels overall don't change our tool at all. But I'm going to stick with the Roman letters for our discussion. So what I'd like to be able to do is build a tool that talks about the sine, cosine, or tangent of angles A, B, and C to build a relationship between sides A, B, and C, even though this isn't a nice right triangle. And it might seem like cheating, but we're going to do that by dropping an altitude, as it's called, from one of the vertices down to its opposite side at a 90-degree angle. So I wanted to break away from 90 degrees. How are we doing that? Well, step one, make a 90-degree angle. So that might seem like I'm cheating, but I do need to relate our tools to this new thing. So our tools are dependent on that 90-degree angle. Now, I've done that specifically with angle C, but certainly we could have done that with any of the other sides. Even if this isn't a nice 90-degree angle, if we could imagine extending that line, then we could just as nicely drop an altitude from B down to the extension of that side where it's 90 degrees, wherever that 90 degrees happens to be. We could do it from A as well, whether that, depending on how it lines up, that altitude might land inside the triangle, it might land outside the triangle. If it's a 90-degree triangle, it lands exactly along the side B. But we could drop this altitude from any of the sides. I'm dropping it from C mostly just for the clarity of this diagram. But you'll see in a minute why it's nice that we could extend this argument to any of the vertices, not just the one at C. Okay, I want to label that altitude H for height. It is often referred to as the height of a triangle. Okay, that breaks our diagram essentially into two smaller triangles, both of which are 90 degrees. So that allows us to use the tools that we've built. So if we want to consider this smaller triangle, which one of our arguments, or we ask ourselves, which one of our arguments can we make about this smaller triangle? Well, if we tried to make an argument about angle C, this small triangle doesn't contain all of angle C. Part of angle C is here, but part of angle C is in the other triangle. So we don't have all of angle C, so I can't make an argument about angle C. Angle B is way over here, so no arguments about angle B. In this small triangle, it's got to be an angle A argument. Okay, so we're going to make an argument about angle A. In reference to angle A and the small triangle, we know its opposite side is H, in the small triangle, and the hypotenuse of the small right triangle is B, this adjacent side to A contains length C, but not all of it, and certainly not half of it or any proportion of it we could tell by the diagram. So we can't use the adjacent side. We're stuck using just the opposite and the hypotenuse. Luckily for us, we know an argument about opposites and hypotenuses. We know that the sine of that angle A would be equal to that height H in ratio to the side length B. Okay, so good. We have an argument. It does reference this altitude that we kind of made up in there. There has to be an altitude there. We might not know what it is, but it references that H there. But still, it's an argument based on what the tools that we already know. We could do the same thing with the second triangle. The second triangle, we can't use angle A anymore, but we could use angle B. And similarly, for angle B, we don't know the side length associated with C in our small triangle, but we do know in reference to B, the opposite side is H and the hypotenuse is A. So we could similarly make an argument that the sine of angle B is equal to that height H in ratio to A, because sine is still opposite over hypotenuse. Now, those arguments might not seem terribly significant, but because they both include that height length, we could solve both of these for that length H. Whether we know that length H or not, we know that length H has to be equal to both B times the sine of A and A times the sine of B. So if those two are both equal to the height, then they must be equal to each other. B times the sine of A has to be equal to A times the sine of B. Furthermore, if we manipulate this just a little bit by dividing the A's and B's over, it's not actually necessary, but it's standard convention. Technically, what we're doing is dividing both sides by A times B, just to put the A's and B's back on the same side. We get a relationship that ends up being super helpful. The sine of A in ratio to the side length A has to be equal to the sine of angle B in ratio to its side length B. Now, before I show you how helpful and cool this tool ends up being, I want to remind you that we could have just as easily dropped an altitude from A or an altitude from B and built two triangles and done this same argument. Because we dropped the altitude here from C, we got a relationship between A's and B's. If we had dropped this altitude from A, we'd have a similar relationship between B and C. If we'd have dropped it from B, we'd have a similar relationship between A and C. So we could have built that the sine of A over A is equal to the sine of C over C instead. Or if we dropped the other altitude, we could have had that the sine of B over B is equal to the sine of C over C. So this argument is really consistent across the entire triangle. That the ratio between the sine of an angle and its opposite side, that ratio of opposites, I'll refer to them as opposite pairs quite a bit, the sine of the angle and its side, that ratio is constant throughout the entire triangle. The ratio between the sine of an angle and its opposite length is constant throughout an entire triangle. So if we have a triangle and we know that, say, oh, this is a 30-degree angle and this length is 10 and this length is 7, we can figure out everything else about that triangle using this relationship, this truth. We don't have to construct the altitudes and build all the pieces. We have the relationship down. So just the fact that the sine of that 30 degrees in ratio to the length 10 has to be equal to the sine of, well, it would have to be this angle. I'm going to call it angle B for the fun of it. B in ratio to its opposite 7. The fact that those have to be equal allows us to solve for B. And we'll do that in a minute. But it didn't have to be that relationship. Let's say we knew that that angle was 30. And why is this diagram so small? I need a bigger triangle. This is a big tool, big triangle for it. That's why, because it's hard to get them to match up. Cheated. So let's say this angle was, say, still 30 degrees and this other angle was 105 degrees. Well, if we know one of the sides, let's say we know this side was 12 units, I'm going to say 12 inches, and we wanted to figure out this other side, again, we can use this tool. We know opposite pairs, their ratios are going to be the same no matter what. So those opposite pairings, the ratio between the sine of the angle and the opposite side has to be constant. So if we want to find this side length, well, we need its angle opposite. Now, we don't know its angle opposite directly, but can we figure out this other angle? That's 105, this is 30. We know the angles in a triangle have to add up to how much? 180. That's right, they have to add up to 180.
180.
Thank you, Sam, I appreciate that. So the 135 plus, what would it have to be, 45? So that's got to be a 45-degree angle. So what do we know? We know that the sine of the 105 degrees in ratio to the 12, that ratio has to be equal to the ratio between the sine of 45 degrees and that unknown side. I'm going to go ahead and keep calling it question mark. Nah, I don't want to call it question mark. I'm going to call it B. B. And this we could certainly solve for B. Multiply both sides by B, multiply both. Can we just flip these equations or flip these expressions in an equation? Does it have to be true that if this is true, then the reciprocals have to be equal? If two fractions are equal, are their reciprocals automatically equal? I see two very reluctant nods of yes, you're trying to figure out what the counterexample is or what the trap is. As long as neither of them are equal to 0, yes, the reciprocals are equal. Fair? That's the only caveat, is that they can't be equal to 0. And it just makes it easier to solve. Frankly, a lot of people, well, I don't know if a lot of people do it. I do it a lot. Look at this tool that we built in two ways. You either have this relationship, or you can look at it just as truthfully as the ratio between the sides and the angles instead of the angles to the sides. So whichever form is handier, use. This is usually the formal way we lay out this tool. But if you're looking for a side length, this is often handier. Use it that way. Fair? But either way, multiply both sides by the sine of 45 here, and we'll get 12 times the sine of 45 degrees over the sine of 105 degrees. And that ratio will give us our side length B. Nicholas, you said no? What was the no in reference to? I'm sorry. I don't know what question I was asking when you said that. Oh, whether reciprocals are the same? As long as they're not 0. And we can prove that real quick if you want. If you have that A over B, I don't want to use A's and B's, I'm using A's and B's for everything else. If you have that, say, N over M is equal to U over V, then we can certainly multiply both sides by MV. Multiply both sides by MV. The M's will cancel, the V's will cancel. So we'll get Vn equals Um, and then divide both sides by, what are we dividing both sides by? Un. Then the n's cancel and the u's cancel. So Vu is equal to Mn. So if these are true, then the reciprocal is true. Again, the only caveat there is that U and N, the things we divided by, can't be 0 because we're not allowed to divide by 0. So as long as neither of these were 0, so neither fraction is 0, we can set them equal to their reciprocals. So it's just a quick little proof with that one little caveat. We can flip over both sides. Now, that doesn't mean a reciprocal is the same as itself. If you have, is x over 5 the same as 5 over x? No. But if x over 5 is equal to 4/3, then 5 over x is equal to 3/4. That is true. Cool. So it's not that these all have the same value. This doesn't have the same value as c over sine c, but the ratios are still equal. Nicholas, does that make sense? Cool. Okay, you guys have had plenty of time to figure out what B is down here, right? What's B down here? Or were you so engrossed by my argument about reciprocals that you didn't have an opportunity? 8.7. Thank you, Nicholas. 8.7. So, boom, that side length's 8.7. And it wasn't a right triangle, but we were still able to find it. We can even find this other side. And we can use the same argument. I'm going to start it in the reciprocal form, though. We still know that the 12 in ratio to the sine of 105, that opposite ratio, has to be equal to, this time, we'll use the other side. So C, or call it A, call it whatever you want, they're just labels. This A has to be equal, well, this A in ratio to the sine of its opposite side, in ratio to the sine of its opposite, has to be equal. Okay, so this time it's 12 sine 30 over sine 105 equals A. But those are just numbers. We can find out what the 12 times the sine of 30 divided by the sine of 105 is. What is it? No, it's not. Sorry, Shay. There's no way that side like 68 inches. You might be in you might be in radians. Yeah. Usually when a number's crazy like that, it's just the mode. You knew it wasn't 68 inches long. Right? Oh, you guys are so slow. Why are you guys so slow? You guys aren't helping. 6.2. That's much more reasonable. I'll have to bring up my calculator. All right. So 6.2, 6.2. That number seems nice and reasonable. So we're going to play with some examples of this tool, but that's the basics of this tool. As I said, this tool ends up being super handy, very significant for quite a lot of other things that we're going to do. It is so significant, it's actually referred to as a law. This is the law of sines. It even comes in sparkly letters because it is a big, big, big important tool. That was supposed to delete. How about cut? Yeah, that'll work. Okay. So, anything about the basis of this tool before we play with some examples? Examples are always good. Everybody likes examples, right? All right. So, let's go from there. So, let's say we've got a nice triangle. We don't know much about it. Again, the one requirement that this tool has is that we need to have an angle, let's say, oh, I don't want to use 105 again. How about, let's say this angle is 85 degrees. We have to have an angle and at least one opposite side. So 42. We've got to have an opposite pair. Like here, we started with this 105 and the 12. We have to have one of those ratios. Because again, what this law of sines tool tells us is that that opposite pair ratio is going to be equal throughout the triangle. So we have to have at least one opposite pair to establish that ratio. And then we know it's going to be equal for everything else. To determine everything else, all we have to know is one other piece of information. That other piece of information can be another angle, like it was here. We can know, say that's 25 degrees. Or that other piece of information can be a side length. And we'll do a problem like that next. So we still need 3 pieces of information. Before, we had 3 pieces of information with our triangles because we knew 2 lengths and a right angle. We could be told this length and that length. We could be told lengths B and A. We could be told any 2 lengths because we knew one of the angles. Here, we still need 3 pieces of information. It just doesn't have to be that one of them is a right angle. So take a minute, use this tool. I'm going to give you 2 minutes. Take this tool and use it to find this other side length and this side length and this angle in whatever order you choose. I'll give you a little more than 2 minutes. 3 numbers you need to find. I'll give you 3 minutes. I just want to yell time really loud and see if anybody jumps. Particularly while Shay is drinking water. Having a rough class today, Shay. Well, we do have some choices here. We could finding this can't find this side over here first. So we can't find that one first because we don't know anything. We don't know its opposite. We don't know it. We got nothing. We could find this side first if we wanted to, or we could find that angle first because they have to add up to 180. We might as well find this one first. What does that have to be? Let's see, that's 100, 110, so that has to be, what, 70 degrees? Yeah, 70 degrees, okay. So we didn't have to do that one first, but yeah, it's easy to quickly bust out. So now that we have that 70 degrees, frankly, we could find either of the sides first. Doesn't matter which. Let's go ahead and find this one next. So what's our ratios? This ratio is given. That ratio, we are given the 85 and we're given the 42. So that's actually going to be our strongest argument. Anything we can make based on any argument or any value we can find based on the 42 and the 85 degrees is going to be stronger because those are given values, not approximations. So we want to use that as much as possible. So we know that has to be equal to the side we're looking for. It doesn't have to be called A's and B's and C's. We could call it W. It doesn't matter. Don't get fixed on these having to be A's, B's, and C's or alphas, betas, and gammas. So I'm going to call that side W because I want to, in ratio to the sine of 25 degrees. So again, our solving is then generally fairly simple. The sine of 25 degrees over the sine of 85 degrees is equal to W. And then that's just a value that we can ask our shiny boxes for. What is 42 sine 25 divided by sine 85? 17.82. 17.82. Can somebody either confirm or argue with that?
That's the same number I got. I rounded it to 4 decimal places, though.
Yeah, I'm going to go with the 82. Just don't have to write that much. But good. And boom, that's it. That's that side, 17.82. Isn't this a nice tool? It's certainly not going to betray us in about 5 minutes. So we've got, let's find that other side real quick. We could now use the 25 degrees and the 17.82, but again, whenever you can use given information, you're better off. So even though we could use the other sides to find that, I don't want to, because anytime you can make an argument based on given information, you're better off. Now, the 70 wasn't given, but we have no choice but to use the 70. For the 42 and the 85 versus the 17.82 and the 25 degrees, we have a choice. So we're going to use the given information because it's going to make us more accurate. Particularly when you're dealing with angles over long distances, even not that long of a distance, can cause pretty dramatic inaccuracies. So the more accurate we can be, the better. So 42 sine 70 degrees over sine 85 degrees. Again, we can calculate that. And what do we get? 39.62. 39.62. And in scale of our 42 and 17 and such, that seems like a perfectly reasonable number. Again, anybody want to back her up?
Yep.
Cool. And if you did the 17.82 and the 25 degrees, you should have gotten essentially the same number. Might round a little bit differently, but essentially the same value. So great. Cool tool. It's not betraying us at all. Awesome. I do want you to notice something. It's true for both of these triangles, and it's actually true in general. Notice the smallest angle here. The smallest angle is creating that small side. The medium-sized angle created a medium side length. It's the middle of the three side lengths. The largest angle created the largest side length. That's true over here. The 30 degrees made the 6.2. The 45 is a little bit larger, 8.7. The 105, the big angle, made the big side length. This is always going to be true in a triangle. The smallest angles opposite the smallest side, the medium angle opposite the medium side, the big angle opposite the big side. That can be very handy to know. Fair? Bigger by how much? Well, that's what the trig functions are doing. The trig functions are finding those ratios. Questions about that example before we look at a different example? So far, we've been given more angles and less sides. We got to switch that up. Okay, I'll take that as you guys are good. Okay. So, need another triangle here. Often you'll see very generic triangles when you get these problems. And often there's a little note somewhere that says, note, triangle not to scale. Never assume the triangles are to scale. Oftentimes just somebody has grabbed the triangle making tool and said, hey, look, we have a triangle. So never assume there's any scale truth to it. This side could be, 4 times the length of the other side. So never, ever assume scale. So let's say we've got that nice triangle, and let's say we know, again, this angle, let's say it's 40 degrees. But let's say we know this side length. What do we want this side length to be? Oh, how about 10? And if I knew the side length of the base down here at the bottom, then I wouldn't have an opposite pair and our tool wouldn't work. We're going to have to fix that in a day or so. But if we had the other side, we'd have an opposite pair and we'd be ready to go. So let's say this other side length is 9. Okay, we have an opposite pair, which means we have enough information to find this angle down here. And our tool that's up there somewhere tells us that the sine of that angle, since I'm looking for an angle, I'm going to leave it on top. The sine of that angle B in ratio to the 10 should be equal to the sine of the 40 degrees in ratio to the 9. That those opposites should be equal in ratio. Now we can certainly solve that for B, right? Now I really, really want everybody to do this. If you don't have your calculator yet, go get it. I want you to solve this for B and write down what you get. I.71. 0.71. The 40 was given in degrees, so your answer should be in degrees, and that looks like you were in radian mode, which means your calculator thought the 40 was also in radians. So careful about mode. We're switching back to talking a lot in degrees. We'll do radians for these as well, but I'm just going to stay in degrees for right now, so careful about that. So, Martin, Nick, Garrett, Sam, Jay, for the first part. What are you guys finding when you solve that for B? I mean, presumably you're multiplying both sides by 10. Sine of B is 10 sine 40 degrees over 9, right? What are you guys getting? In degrees? Really? Oh. Nicholas, I'm sorry then. That's really that? No. It's 0.7 degrees. Really? Oh, because that 9 and 10 are so close. Oh, well, no. Is that really? That's crazy. If so, I totally apologize, Nicholas. I'm in degrees, really? Not that I don't believe you guys, but clearly I don't because I signed for it. Now, how is that? No, that's not true. I'm all flustered here. Let me check this. Mode, put myself in degrees.
I think I solved for sine B instead of B. So
Yeah, don't find sine B. Find B. Angle B. Okay, that makes more sense because it's like there's no way that's true. Yeah, finding the actual angle. B. So I'm not sorry anymore. But I am sorry about the argument about radians. Yeah, that's the ratio. But
we
what's
have
the
to take
actual
the
angle?
inverse of each side to get rid of the sine, so it could be B equals something.
Yeah. How do we get that sign to go away? We know how to do that, right? Throw it. I have an autocorrect apparently now. Throw in a sine inverse there. And a sine inverse. You guys know how to solve in trig. That was last test. You guys, should I maybe look over that test again, see if you guys should lose some points for your solving? So what should happen? Nicholas, that sounds better. And it's degrees, okay. Anybody else? Because Nicholas, that's better, but it's not quite the answer for B? Martin, what about you? What are you getting when you find the angle? Nick, I know you're there. Garrett? What are you getting? Or are you agreeing with Nicholas? Nick, you're agreeing with Nicholas? Okay. Sam, you're messing with your approximation, but same basic answer. No. Samuel, you said we're using an inverse function here, right? When we use an inverse function, how many answers do we get? 2 answers and all the coterminals. So your 45 and a half, your 45 and a half ishes aren't wrong. They're correct. They're just incomplete. We're being told that could be 45 point, I'm going to just round that to 6 degrees. But we know when we solve, we technically get infinitely. Why is that? Oh, it's because this is on. We technically get infinitely many answers. So 45.6, but also we're going to get another one, 180 minus the 45.6. So it's going to be 100 and what, 34.5, 34.4 degrees. Can a 134-degree angle live in a triangle? It sure can. Be an obtuse triangle.
Yeah, it's within the bounds.
It's within the bounds. Now, you might look at that triangle and go, yeah, but it's not going to fit in that triangle. Is that triangle drawn to scale? Very much no. So this is actually going to break us into 2 possible triangles here. It could be that that's a 10, a 9, and a 40-degree angle with a 134.4-degree angle there, or this triangle with the 10, the 9, the 40, and the 45.6 degrees. Both of those triangles satisfy what we were told. Both of those are valid triangles for these 3 pieces of information. So if we're asked to find all the other sides for the triangle that this might be, we end up with 2 answers. We end up with 2 triangles. Okay, here, the 134.4 and the 40 wouldn't leave us much. That would be, what, 6, so 5.6 degree angle up there. Where here we'd have a, what, 94.4 degree angle? But could we find that other side length given that? Yes, we could. Could we find this other side length given that? Yes, we could. So this is going to happen to us sometimes when we're using law of sines. That we have to deal with the fact that when we use the inverse function, how many answers do we get? I've mentioned that before, right? When we use an inverse function, we get how many answers? Now, we still do technically get the coterminals, the plus 2 times 180 degrees, but they will, the bigger ones will never, why am I not 2 times k times? Sorry. Why 180? Oh, that's why. It doesn't matter. k times 360 degrees. That's why I had a 2. K times 360 degrees. But none of those will ever fit in a triangle. But our principal inverse and secondary inverse both are possible for triangles, so we have to consider them. If we forget them, planes crash, bridges fall down, satellites slam into stuff. The world slowly perishes. So we'll look at some examples of that tomorrow. You guys have to go today, but we'll look at some examples of handling that tomorrow. This is generally referred to as law of sines ambiguous case. So if you want to look that over before tomorrow, great. But we'll talk about this more tomorrow and talk about some of the other cool things we can do with this tool. Questions before you guys go? Thank you, Nicholas Martin, for helping out today. Sam and Shay, thank you too for helping out today. Nick, thank you for helping out today. It's helpful when you guys talk or type or whatever. Anything I can do for you guys? All right, go forth and play with these things. And again, good job on that exam. You guys kicked the crud out of it. The average was like 89%. So have a wonderful day.